In this lecture 17, I will discuss about the settlement calculation of shallow foundation. So, last class I have discussed immediate settlement, then the consolidation settlement. So, these are the consolidation immediate settlement I have discussed in the last class. Then how to get the influence factor IF, I have given the table also, and then what would be the probable ranges of elastic modulus of soil, different soils, and how we will calculate the elastic modulus of soil, and what are the possible ranges of Poisson ratio values are also given in the last class lecture. So, in this class I have already discussed in the last class about the consolidation settlement. So, these are the two possible ways we can determine the consolidation settlement depending upon the values or the parameters available. So, these are the expressions we have to apply for different layers. So, that in the immediate settlement, if it is rigid foundations, so we have to apply two corrections, rigidity corrections and the depth correction, and if it is flexible foundation or the isolated footing, then you have to apply for the depth correction. Or in the consolidation settlement, you have to apply for three correction: rigidity, consolidation and the pore water pressure correction, because our consolidation equation that we are using, it is 1D consolidation equation, but the consolidation process is actually a 3D process. So, we have to apply a correction that we have to get that correction factor from the chart or the available values that I have given in the last class. So, these are the available values for different soil of this correction factor, and if the parameter A is available, then from this chart also we can determine this correction factor. So, these things already been discussed. So, this is as per the IS code. So, in the so if I that is the correction factor for the pore water pressure. So, now we have the two more corrections, one is the rigidity correction of the foundation, another is the correction for the depth factor, and so the rigidity correction factor, we will get the total settlement of rigid foundation divided by the total settlement of center at the center of flexible foundation. So, generally the correction factor is taken as 0.8. So, when we calculate the influence factor in the table, if you notice that table, then you will find that the influence factor at the center of the flexible foundation and influence factor at the rigid foundation or the wrap foundation. So, then you will find that the rigid foundation's influence factor is around 0.8 times the influence factor of the center of flexible foundation. So, in the rigidity correction, we take the 0.8 as a rigidity correction. So, we will calculate the settlement considering the footing as a flexible foundation, and we will use the flexible foundation values, required values, and then we apply this rigidity correction 0.8 for the rigid foundation, because here the settlement will be less as the foundation is a rigid one. So, that rigidity effect we have to consider. And then the depth factor, also we can get depth factor from this chart. So, this chart is given in IS code IS 8009 part 1 1976. So, how we will use this chart? This chart or these corrections is called the Fox corrections for the settlement. Okay, for the flexible rectangular footing of L by B at a depth of D. So, that also, as we have mentioned, that we are using all flexible foundation correction factors, but ultimately for the rigid foundation you have to apply the 0.8. So, for the rigid foundation also for depth correction we will use this chart. Now, for this chart, so there is a term D. So, this D is actually the DF, depth of the foundation. L is the length of the footing, B is the width of the footing, and so this is dA, and these lines are developed for L by B. This is for the 100, this is 25, this is 9, and this is 1. And this is a two part. So, this is one is dF root over L by B, another L by B root over dF. So, now this chart, the lower portion of this chart can be used for the foundation whose depth of foundation is high. Okay. So, relatively higher depth of foundation we can use for this lower chart, and for example, when you calculate the pile foundation settlement calculation, we may use this lower portion of the chart. So, this is for the relatively higher depth of foundation, and but most of the cases in shallow foundation we will use the upper portion of the chart, where this will be dF root over L by B. So, if I know root over L by B, if I know the L by B value, then from here, suppose for the this dF root over L by B 0.6, if the L by B value is 1, so the correction value will be around 0.85. So, this is 0.85. So, this will be 0.825. So, this will be the correction factor value. So, this is a 0.825. So, corresponding to dF, if this value is 0.6 and L by B is equal to 1 or the square footing, then we will get this correction factor as 0.825. So, this is the depth correction factor. So, the settlement calculation that we have discussed, that this is for the immediate settlement and the consolidation settlement. So, these two methods are generally used for the clay soil, because obviously consolidation settlement will be used for the clay soil, and the immediate settlement that we have discussed, that also we use for the clay soil, because in the clay soil also we will consider the immediate settlement, though it will be less compared to the consolidation settlement, but during the total settlement calculation we will calculate the immediate settlement as well as the consolidation settlement of the clay, and then we will add. And another thing I want to mention, that in this course I will discuss only the consolidation settlement for this primary consolidation settlement. The third one, that is more useful or applicable for the organic clay. So, that we will not discuss here. We will discuss here mostly these two, immediate and the primary consolidation settlement, because these two are very common in this soil mechanics, and so we will use these two, and our soil are according to that we will choose that, mean whether it is the inorganic type of clay, where these consolidation settlement and the immediate settlement are the two major factors, and for the sand the immediate settlement is the major factor. But when you are talking about the settlement of sand or the granular material, then we have to use the field test data rather than using the laboratory test data, because as I have already mentioned that the getting undisturbed soil sample is possible or easy for the clay soil. So, in the clay soil we will get the undisturbed soil sample, and then we will test this soil sample in the lab, and then we will get the properties. Those properties I will use for our settlement calculation purpose. But in the sandy soil, getting the undisturbed soil sample is difficult. So, that is why we will rely on the field test for the consolidation, for that settlement calculation. So, I will discuss that what are the first method, that what are the methods that we are used to determine the settlement of a granular soil. The first method that we are talking about is the plate load test method. So, it is not only the settlement, the bearing capacity also we can determine by using the plate load test. So, this is the field test. So, till now the methods that I have discussed all are theoretical methods, where we have to use the soil parameters, and then we will get the ultimate bearing capacity or the settlement of the foundation. But this the plate load test, here in the field itself, by the field test data we can determine the bearing capacity or the settlement of a foundation. Also that is the advantage of the plate load test. So, that we are testing it on the field where the foundation will be constructed, and from that data we are using for the foundation design. So, that is the advantage of the plate load test. So, what is plate load test? This is a plate load test. Instead of using the real foundation, we are using a plate on which we are applying the load, and then we are measuring the settlement. So, this plate is treated as a foundation, and ideally the depth of the plate where we are placing this plate, the depth of the plate should be equal to the depth of the foundation. But sometimes it may not be possible. So, in that case, when you use this data, we have to take the proper precaution, or you have to apply the depth corrections. If your place of the placing depth of the plate and the depth of foundations, they are not same, but ideally it should be same. So, here also we placed, so that means I have to construct a pit. So, this is the pit, and this is basically the depth of the plate, or that should be ideally depth of the foundation. So, this is the df or dp, depth of the plate. So, this is the df, or you can say this is df or dp, depth of the plate. F means the foundation, p means the plate, and this the pit width should be at least 5 times the width of the plate. So, this is the plate. So, this is the plate, and the width of the plate should be 5 times the width of the pit, should be 5 times width of the plate. So, now reaction frame is placed. So, with the help of this reaction frame, a load is applied through a hydraulic jack, and this pressure gauge or the dial gauge is used. This pressure gauge or the proving ring is used this to measure the load that is applied, and this dial gauge will measure the settlement of the plate. So, that means we are applying load and we are measuring the settlement. So, that means this dial gauge is used to measure the settlement, and generally we apply 2 dial gauges to opposite corners of the plate. So, that means if this is the plate, so we place 2 dial gauges, one is here, another is here, or here, or here, 2, and then we take the average of these 2 values as the settlement of the plate. And then if I see, this is the photographs of the plate load test. So, this is the plate where it is tested, and this is again, this is the trench or the pit where the plate is placed, and these are the reaction frames. These are the sandbags where this load is applied, because this hydraulic jack is giving a pressure on this frame. So, that is giving the reaction. So, we should have a sufficient weight over this over this reaction frame. So, that means here we have to apply the load, and these are the dial gauges. So, the dial gauges are used to measure the settlement, and sometimes these proving rings are also used to measure the load that is applied, and here load cell can also be used to measure the load. Sometimes in place of dial gauge, LVDT can also be used to measure the settlement. So, ultimately we in a plate we are applying a load and we are measuring the settlement, and this is done in the field. So, this is the total procedure of this plate load test. So, rough mild steel plate. So, generally keep in mind that the minimum plate size should be used 30 centimeter. We cannot use a plate size which is less than 30 centimeter, because this is not recommended. Less than 30 is not recommended, then we will not get the appropriate result. And the other plate size are 40 centimeter, 60 centimeter and up to 70 centimeter, either it is square or circular in shape. So, when we place the plate on the ground, 5 millimeter fine sand is placed on the ground, on the pit, and then we place the plate. So, this will give a smooth contact between the soil and the plate. The generally smaller sizes of plates are used for dense or steep soil, and larger size are used for the loose and the soft soil. Now, water is removed by pumping out. If in the trench there is water, so you have to remove the water to conduct the test. So, that means the loads can be the loads on the test plate may be applied by gravity loading or the reaction frame that I have already discussed. So, to the reaction frame we apply the load, and before we apply the actual load, a sitting load of 70 kg per centimeter square is first applied and then released after some time. So, this sitting load will help this plate to make a contact or perfect contact with the soil and the plate. That is why this sitting load is applied. Then load is applied at 1/5 of estimated shape load or up to the failure or at least 20 millimeter settlement, whichever is earlier. So, it means that before we do the plate load test, so we have to know the properties of the soil of that site, and based on that property, by using the available theories for bearing capacity, you have to determine the safe load capacity of that plate on that soil. So, and we have already discussed the available theories. So, based on that, if we know the C and phi or the strain properties or the unit weight of the soil, then we can determine what would be the safe load, and then we have to apply the 1/5 of that estimated safe load up to the failure or at least 25 millimeter settlement. Suppose if the safe load is 100 kilonewton per meter square, then we have to first load increment that we have to apply is 20 kilonewton per meter square, or if the total load is 20 kilonewton, then the first increment of load will be total load is 100 kilonewton, then first increment of load will be 20 kilonewton, then next one will be the 40 kilonewton, then next one will be the 60 kilonewton, like that. So, that means 1/5 of the safe load of that plate. So, that how we will get the safe load? By using the available bearing capacity theories. So, we have to get the soil properties for that. Now, for the each load, when we apply the each increment of each load, the settlement is recorded in the time intervals of 1 minute, 2.25 minutes, 6, 4, 6.25, 9, 16 and 25 minutes interval, and thereafter every hourly we have to take the load reading. So, that means we first apply, say for first application say 20 kilonewton we applied, and then we record it for 1 minute, 2.25 and 4, like this interval, and then up to 25 minutes, then every 1 hour we take the reading of the settlement. We are taking reading means we are taking the reading of the dial gauge or the LVDT to get the settlement. We are measuring the settlement. So, and then for the clay soil, this load is increased when the next increment is applied, when the time settlement curves indicate that settlement had exceed 70 to 80% of the probable ultimate settlement or at the end of 24 hours. So, what does it mean? It means that if the soil is sandy soil or granular soil, so that means there all the settlements are immediate settlements. So, you will get the settlement immediately. So, after say a few hours you will find or that there is no further increment of the settlement or for no further significant increment of the settlement. So, they are depending upon soil or depending upon the site condition, may take say few minutes to few hours, but if it is granular soil, because the range is 0.205 millimeter per minute. So, if your settlement range reaches this limit, or if it is less than that, that means there is a change in settlement is 0.02 millimeter per minute, then we will stop. So, for the sand we will get this thing very early, because because most of the things are immediate settlement. But as I mentioned, this test is also suitable for the granular soil, but for the clay also we can use this, we can do this test also in the clay. But as the clay, the most of the settlement are the consolidation settlement, and this type of test is a short term test. So, for the long term settlement, it is not not very useful to use these things for the long term settlement, because we will not get the long term settlement, because we are doing this test for the short term. And for but clay has the long term settlement. So, in case of clay, so first for a particular load, and if we apply on the plate, so for that particular load, what would be the probable settlement, that you have to calculate. You have to calculate by using the previous expressions that I have given, that immediate settlement, and for that load what will be the consolidation settlement. Then you will get the maximum probable ultimate settlement for that particular load. So, if your test reaches more than 70 to 80% of that probable ultimate settlement, or after 24 hours, so whichever is earlier, you have to apply the next increment of load. And again, for the next increment of load, what would be the probable maximum settlement, you have to calculate, and then you have to you have to see whether it is exceeds 70% or 80% of that. If exceed that, then you apply the next increment. This is for the clay. And for the sand, generally we follow that if the settlement rate is less than 0.02 millimeter per minute, then we apply the next increment of load. And in the clay, either 24 hours, or if it exceeds the 70 to 80% of the probable ultimate settlement. So, probable ultimate settlement you will calculate by available the theoretical expressions for immediate and the consolidation settlement. So, next one, the settlement are recorded through a minimum of tool dial gauge, and which is placed diagonally opposite to the plate, and load settlement curve for the test plate can be plotted from the plate load test data. So, ultimately the end product of this test, that we will get a load versus settlement plot. So, we will apply the load, we will measure the settlement, and then that we will plot that, and from that plot we will use for our design purpose. Now, after that we will get at the end of the test we will get this type of plot. So, you will find, so cohesive soil we will get, this is the plot for the cohesive soil, this is the plot for the loose to medium cohesionless soil, this is for the dense cohesionless soil, and this is partially cohesive soil. So, this chart is taken from the IS code. But one thing that I want to mention, that that here if you find these different plots, so here we are not getting any peak. So, then to get the ultimate load, I have discussed in the previous class also, either you have to use for the double tangent method or the single tangent method. Here this load is parallel, this load settlement curve is parallel to the settlement axis. So, it is almost parallel to the settlement axis. So, we draw the tangent, the last state portion of the curve, and this will give us the Q ultimate. Okay. But for this type of curve, where it is not parallel to the settlement axis, then the initial state portion of the curve and the initial state portion of the curve and the final state portion of the curve. So, if I extend that, then the intersection point, this is the intersection point. So, corresponding load or the stress will give the ultimate load or the stress. So, this is the double tangent method, this is the single tangent method, by which by using these methods we can determine what would be the ultimate load from the load settlement plot. Then from this plate, ultimately you have to calculate the settlement of the foundation or the load carrying capacity of the foundation. So, ultimately from this test data, so there are few correlations are given between the plate settlement and the foundation settlement. So, this is the correlation first proposed by Tarzaki and Peck. So, by which if I use this correlation, we can correlate the plate settlement with the foundation, real foundation settlement. So, SF means the settlement of the foundation, SP is the settlement of the plate. So, this is the correlation for granular soil. Remember that this is for the granular soil, and if we are using this correlation, then BP and BF, width of the plate and width of the footing, should be in centimeter. So, remember that this should be in centimeter. Okay. So, and this is applicable for granular soil and for the footing. So, we can use this correlation to correlate the plate settlement and the foundation settlement or determination of the foundation settlement. So, next one is for the important consideration. So, as I mentioned that we cannot use the plate size less than 30 centimeter. So, I mean then we will not get the appropriate or proper results. Another very important thing that this test is suitable for the homogeneous soil. For the layered soil, then this test will not give the appropriate result, because if it is a homogeneous soil, then influence of the real foundation and influence of the plate will be on the same soil, because the size of the plate is say 30 centimeter, or then the real foundation size say 2 meter. So, as I mentioned, for the settlement we will go the influence zone up to twice B. So, for the say real foundation, the influence zone is up to 4 meter below the base of the footing, but in the real plate the influence zone is only 60 into 2. So, that will be 120 centimeter. So, if it is a homogeneous soil, then it is fine, because both the cases this influence zone is the same soil. But if it is in layered soil, then it may be a possibility that for the plate your influence zone is only in the top layer, but in the actual foundation influence zone may be in the other layers also. Those effect of those layers are not incorporated, are not in the plate load test. So, those effect you are not getting into your plate load test result, because your plate loading influence zone is not reached up to those layers. So, that is why you may not get the proper result. And then the capillary in sand bed increases its effective vertical stress or stiffness. So, the test will result in a reverse severe estimate the actual settlement. So, if there is a capillary lies, then you have to keep in mind these things, that your result in a severe underestimate the actual settlement. So, you have to take care in that case. So, these are the things. So, these are the, so it has some advantages. So, we will get the data from the field itself, but it has some limitations also. These are some limitations. Another one, in the clay soil, we know the consolidation settlement or the time dependent settlement or the long term settlement are the major thing, but here we are getting the immediate settlement. So, so if I use this settlement, so then we have to use these expressions. So, this is for the, these expression is values for the clay soil. Okay. So, this is the settlement of the footing, this is settlement of the plate, and this is the width of the footing, width of the plate. So, this is applicable for the clay soil, though it will give you the immediate settlement. So, Next one is in terms of ultimate bearing capacity calculation from the plate load test. So, for the cohesionless soil, so the ultimate load carrying capacity of the foundation and the ultimate load carrying capacity of the plate can be correlated with the width of the plate and the width of the foundation. So, this is the correlation for cohesionless soil, but for the cohesive soil, as I have already mentioned, that the cohesive soil, your net ultimate load or the net ultimate is not function of width, even your ultimate load is the function of depth only, but it is not function of width. So, none of the cases, whether it is the ultimate load or net ultimate, so your bearing capacity for clay soil is independent to the width of the footing. So, that is why here this width is not giving any effect. So, that is why you have the ultimate load carrying capacity of the plate is equal to the ultimate load carrying capacity of the foundation. But remember that your soil should be homogeneous. So, these are the correlations in terms of bearing capacity. Now, how I will calculate the safe bearing capacity from a plate load test. The safe bearing capacity of a footing can be determined from the load settlement curve of the test plate. So, if you have a load settlement curve, from that load settlement curve we can determine what would be the safe bearing capacity from the plate load test data. Now, how we will do that? So, if we have the permissible settlement of a footing, real foundation is say SP. SP is the foundation of a permissible settlement of foundation of width is the SP. Okay. So, this is not the plate. So, this is the permissible settlement. Okay. So, this is the permissible settlement of a real foundation width of BF. Now, what will be the settlement? This is the settlement of the plate. This is the because here both the cases SP is used. So, that is why. So, from this permissible settlement, what would be the settlement of the plate that we corresponding to this permissible settlement, then we can determine these things by using the correlations that we have just discussed. So, now from this correlation you will get what will be the settlement of the plate corresponding to the permissible settlement of the footing. Then from the load settlement curve, with respect to that settlement of the plate, we will get the intensity of load, and that intensity of load will give us the safe bearing capacity of the foundation or the safe bearing capacity from that load settlement curve. So, this will so that is why the load settlement curve can be used to determine the safe bearing capacity of the soil, as well as it can use the settlement of the foundation also. So, ultimately we can use this test data for our design purpose. So, next one, that in the safe bearing capacity calculation from the plate load test, we have to apply the corrections factor, because till now we have considered that there is no water. So, water effect we have not considered, but if we think that there is the possibility of water table rise, then we have to consider the water table effect also. So, that means how we will consider the water table effect? Now, for the actual settlement of a foundation, that will be the settlement that we are getting from the plate load test divided the correction factor. Remember that there is one thing is that when we are applying the correction factor for the bearing capacity, we are multiplying that correction factor with the bearing capacity, because water will also always create a negative effect. So, if the water table height increases, or the position of the water table increases, then what will happen? That your bearing capacity value will decrease. So, that is why you have to multiply the bearing this correction factor, and these correction factors are always less than 1. So, maximum it varies, maximum value is 1. So, it is always less than 1 or 1 depending upon the position of the water table. So, in case of bearing capacity, as the water table reduces the bearing capacity, so you have to apply the correction factor, you have to multiply the correction factor with the bearing capacity value. But in case of settlement, here also it will create the negative effect. So, here you have to divide it, so that your amount of settlement will increase due to the effect of water table. So, that is why in case of bearing capacity you have to multiply the correction factor, in case of settlement you have to divide the correction factor. So, that is the case here, it is the settlement. So, we have to give the correction factor or to multiply divide it by the correction factor. And this correction factor we can get by two methods. One is Pick, Hansen and Thorman 1974, and where df is the depth of water table below the ground level. So, remember that the difference between these two methods, that if this is your foundation and this is the ground level. So, your here df is dw is this one, this is the df, d is the depth of foundation, b is width of foundation. So, any position of the water from the ground surface is called as dw. But as per the IS method, if you look at this method, then if this is the depth of the foundation df, then your dw dash is measured from the base of the foundation. dw dash is base of the foundation. Suppose this is the position of the water table, here this is the position of the water table. So, remember that here this is dw dash means it is measured from the base of the foundation, and dw means it is measured from the top of the or the from the ground surface. So, sometimes dw is limited to the base of the foundation also, but here in this case, so that means the influence zone is up to df plus b. So, that I have already explained. So, this is up to b, here also influence zone is up to b. Beyond the b or depth from the base of the foundation, we do not consider the water table effect. So, here if say water table is at the base, so dw dash is 0, then Cw will be the 0.5. So, and here we can have a different value. So, in IS code, according to the IS code, if your water table is at the base level or above the base level, then the correction factor is always 0.5. So, base level from or above the base level, it is 0.5, and at the B from the base of the footing is 1, and in between base to the B depth we can use this expression. Okay. So, with this I am finishing this today's lecture. In the next class I will solve a problem by using a plate load test data. Then I will show how we can use this plate load test data to determine the safe bearing capacity or the settlement, and how we can incorporate the water table effect. Thank you.